It is the 15th of September 2025, approximately 2:37 p.m. So we're going to be looking at 3.2 exercises. This might be a two-parter because there's 7 of them, and I don't know if I have enough time to make it a one-parter. Yeah, so let's go ahead and, well, this is a big marker. Goodness. So let's get a larger one. And now on to 3.2 exercises, starting with 3.2-1. For that, we have let f of n and g of n be asymptotically non-negative functions. Fair enough. Now, using the basic definition of theta notation, prove that the maximum between f of n and g of n is equal to theta of f of n plus g of n. Wow. Right? Okay. So intuitively, for any non-negative xy, the larger of the two is at most their sum and at least half their sum. Replace xy by f of n and g of n once n is large enough that both are non-negative. Let's think about that a bit. So yeah, so at least if we're trying to look at it in terms of theta, I think that's the case, and then at least half their sum. Let's think about that. Not entirely sure. Let me just think about that a bit more, because I think I may have made some errors in the intuition, but I feel like part of that is true if we, okay. Place xy by f of n and g of n. Both are non-negative. It's kind of fuzzy, but let's see if we can make heads or tails of it by going a bit more rigorously. So since f and g are asymptotically non-negative, there exists n sub 0 and not such that for all n greater than or equal to n sub 0, we have f of n is greater than or equal to 0 and g of n is greater than or equal to 0. Of course, now for any real xy, greater than or equal to 0, we have that the max between x and y is less than or equal to x plus y, which is less than or equal to 2 max x, y. So this is sort of getting at what I was mentioning in the intuition, but I don't know if I phrased it right, and the intuition is my problem. But this is what I was trying to say, is that, well, by definition of what a maximum is, it's either less than or equal to x plus y, and x plus y is less than or equal to 2 times the maximum of what we had earlier. So 2 times the maximum of x and y, right? So applying this, with x is equal to f of n and y is equal to g of n for n is greater than or equal to n naught, that yields something which I might run out of board space for, but it yields the maximum of f of n and g of n. Well, that's less than or equal to f of n plus g of n, which is less than or equal to 2 times the maximum among f of n and g of n. Just barely. Okay. Okay, so we see where this is going. Well, let's erase this and keep going. Just see where it leads. So, by definition, well, actually, let me see. Well, so there exists positive constants c sub 1, which is equal to 1/2, c sub 2, which is equal to 1, and n sub 0 or n naught, such that for all n greater than or equal to n naught, we have c sub 1 times open parentheses f of n plus g of n, close parentheses, is less than or equal to the maximum between f of n and g of n, which is itself less than or equal to c sub 2 times open parentheses f of n plus g of n. And by the definition, right, this should look familiar, so by the definition of theta notation, this proves that the maximum between f of n and g of n is equal to theta of f of n plus g of n, right? So there we go for the first one. All right, let's go after the second one here. Okay, so the next one, 3.2-2, we have explain why the statement the running time of an algorithm A is at least big O of n squared. So this is the statement we're discussing. Explain why the statement, the running time of an algorithm A is at least big O of n squared, is meaningless. So intuitively, big O gives an upper bound. It denotes a set of functions. Saying at least big O of n squared, it mixes in a numeric inequality. So it's like at least with a set name big O of n squared, which has no coherent meaning. If a lower bound is intended, the correct notation is that some big T, capital T of n is within the set big omega of n squared. But that's it's a bit finicky. So let's well, I don't know about that, but it's a bit less precise than what we need. So let's let capital T of n be the running time. The running time of A. And so let's break this down like a high school essay. So category, so for the first part, we have a category error, right? So big O of n squared is a set. You know, put aside the sort of absurd notation that we usually use, right? But it's a set of f of n such that f of n is less than or equal to some c times n squared for n is greater than or equal to n naught. It's not a number, right? So the phrase T of n, the phrase capital T of n, which is the running time, right? The running time of the algorithm A is at least big O of n squared. That attempts to compare a function. Compare a function with a set via numeric inequality. And, you know, take the abuses of notation which come with this information, but whenever we write that such and such a function is equal to this, you know, some big O of n squared, what we're saying is it belongs to the set. That's what that's saying. To say at least that is meaningless, essentially, because of that sort of thing that we turn a blind eye to usually in this case. This is ill-typed. Now, I'm going to need more board space for this, so now, if interpreted as a lower bound, the notation is wrong. So, and because the mathematically meaningful statement is capital T of n is an element of the set omega of n squared, which is to say, that is, there exists a constant c greater than 0 and n not greater than 0, such that capital T of n is greater than or equal to capital C n squared for all n greater than or equal to n naught, right? So now for another thing, if interpreted as there exists an f within the set big O of n squared, with t of n being greater than or equal to f of n, it's vacuous. It's vacuous. What do I mean by that? Well, because the zero function zero of n, that's supposed to be a 0, let's put that there to make sure it's a 0, is within the set big O of n squared, and t of n is greater than or equal to 0 for asymptotically non-negative running times, the statement would be trivially true for every algorithm. And thus conveys no real information. Well, how would I say this? That's not, okay, it's trivially true in the sense that, what is it? Okay. Just kind of funny because all of this formality kind of goes a bit away with the exception of writing an equal sign there, but just kind of, we're looking at this a bit more under a strict lens. But to say it's meaningless though is a bit more harsh than I would give it, but we're trying to play the game here in that sense. So we'll say, therefore, the phrase at least big O of n squared that phrase is meaningless. One must either write the capital T of n is contained within the set big O of n squared, in which case we have ourselves an upper bound, or T, capital T of n is contained within the set of big omega n squared, in the case of lower bound, or T of n is contained within the set theta of n squared, in the case of a tight bound. Can't get anything to any degree of accuracy by saying the running time of algorithm A is at least big O of n squared. So we can't, it's not that, okay, so I think, if I'm not mistaken, that's the way the exercise is phrased. It's phrased, say that statement is meaningless. It's like, prove that statement is meaningless, right? And I would say that it's like, it's not that it's not meaningless, it's just that it doesn't convey any sort of valuable information. Because, right, you can have things that don't convey valuable information, but they still mean something, right? But that's besides the point. Now let's move on to okay, so at least big O of n squared, right? Let me think about this a little bit more. Doesn't. Yeah, I think that's all I have to say on that. Let's go ahead and move forward to the next exercise. There's probably a lot more to say on that, just like the difference in between something that doesn't have any meaning and something that's actually means something, and it's just that the meaning of that thing wouldn't necessarily be valuable in any way. But that's a whole nother thing. So let's just focus on 3.2-3. So, I can't remember if I transcribed that exercise question on there correctly. I'm pretty sure I did, though. So for 3.2-3, is 2 to the n plus 1 equal to big O of 2n? Furthermore, is 2 to the 2n equal to big O of 2 to the n? It's really two questions in one. It's not very fair, but c'est la vie. So, intuitively multiplying 2 to the n by a constant factor only changes the constant in big O, but squaring the exponent, here 2n versus n, multiplies by an exponential factor which outgrows any fixed constant. So, looking at that more rigorously, oops, almost put the actual word I was saying right there. So, for the first case, for 2 to the n plus 1, we have 2 to the n plus 1 is equal to 2 times 2 to the n, which is less than or equal to some constant c times 2 to the n for all n greater than or equal to 1. In this case, we have c is equal to 2. So 2 to the n plus 1, that's contained within the set big O to the 2n, right? Good there. So we can say that little bit of 2 to the n plus 1 is in fact equal to big O of 2 to the n. Okay, now let's move on to the second part. So if I didn't put that last part down, I probably would have been able to put both of them on this. But, oh well. So for 2 to the 2n, we have 2 to the 2n over 2 to the n is equal to 2 to the n, which approaches infinity as n approaches infinity, right? So no constancy, which is the crux of the argument for the previous case, can satisfy 2 to the 2n less than or equal to c times 2 to the n for all sufficiently, let's say sufficiently large n. So therefore 2 to the 2n is not contained within the set big O of 2 to the n. In fact, 2 to the 2n is contained within the set little omega of 2 to the n. So it's just a little bit of a actually, but that's allowed. All right, so let's proceed to the next exercise here. Okay, let me erase this. So this is exercise 3.2-4. And it just says prove theorem 3.1, which is funny because it's like, well, I don't think that it actually restates what theorem 3.1 is there in the exercise, which is just kind of annoying because you kind of have to like flip a few pages back or like scroll a few pages back in order to get to theorem 3.1, but thus is our task. So what is theorem 3.1? Well, theorem 3.1, if you remember, well, actually, yeah, if you remember from the book, states that for any, you know what, I'll just put this in plain English and not just like a, what is it? Fancy it up with a notation. So for any two functions, f of n and g of n, we have f of n is equal to theta of g of n if and only if. So f of n, f of n is equal to big O of g of n, and f of n, right, is equal to big omega of g of n. So if you remember in the lecture, on chapter 3, what I said was, we're not going to prove this right now, or something like that. I must have said something like that. So here's the comeuppance for that, right? We gotta actually prove that now. So intuitively, theta of g means f is eventually sandwiched. Like, it's like the sandwich theorem, essentially. If you look back at calculus, theta of g means f is eventually sandwiched between two constant multiples of g. Being below a constant multiple is exactly big O of g. Being above a constant multiple is exactly big O omega of g. So a tight sandwich, so to speak, theta, is equivalent to having both the upper, big O, and lower, big omega, sandwiches at once. How do we say that rigorously, right? Well, for any two functions, f of n and g of n, f of n is equal to theta of g of n. Well, okay. So, actually, I was just about to restate the theorem, but we don't really need to restate the theorem because we have it right there. What I mean to say is this has left, right, so if and only if, right? So we have to prove it both ways. So for the first way, which is left, right, if f of n is equal to theta of g of n, then there exists c sub 1, c sub 2 greater than 0, and yeah, I remember describing how we'd go about proving this, and this is exactly what we're doing. We're putting it back into the sort of set notation of the entire thing, and then, well, we're going words, and then set notation, and then back to words, in a way. So there exists c sub 1, c sub 2 greater than 0, and n sub 0, or n naught, such that for all n greater than or equal to n naught, we have 0 is less than or equal to c sub 1 times g of n, which is less than or equal to f of n, which is less than or equal to c sub 2 of g of n. So that's all fine and dandy, right? Well, it's only really one way. Well, actually, let me see. Well, okay, so therefore, f of n is contained within big O by definition of big O, by definition of the set of big O of g of n, in which case we use c here to equal c sub 2, and f of n is contained within the set big omega of g of n, in which case we'd use c is equal to c sub 1, right? So we have it proven, we've proven the left to right implication. Now let's prove the right to left implication. I'm going to erase this here. So, right-left implication. So we're assuming, well, let's just say if f of n is equal to big O of g of n, and f of n is equal to big omega of g of n, then there exists c sub 2 greater than 0, n sub 2 with 0 being less than or equal to f sub n being less than or equal to c sub 2 times g of n for all n being greater than or equal to n sub 2, and there exists c sub 1 greater than 0, and with 0 being less than or equal to c sub 1 times g of n less than or equal to f of n for all n greater than or equal to n sub 1. Now, let n naught, or n sub 0, be equal to the maximum between n sub 1 and n sub 2. Well, for all n greater than or equal to n sub 0, or n naught, we have 0 is less than or equal to c sub 1 times g of n, which is less than or equal to f of n, which is less than or equal to c sub 2 times g of n. And this is precisely what we wanted. This is precisely the definition. The definition of f of n is equal to theta of g of n. So QED, this completes the proof. We can move on to the next exercise. Okay. So let's go here. Yes, 3.2-5. Prove that the running time two times you ever talk about running time, either track or computer science. No, there's got to be more than that, but of an algorithm is theta of g of n if and only if its worst case running time is big O of g of n, and its best case running time is big omega of g of n. So prove that the running time of an algorithm. Yeah, and this is okay. So if every input of size n takes time within constant factors of g of n, and certainly the slowest input is less than or equal to a constant times g of n, which would be a big O upper bound, right? So, and the fastest input is greater than or equal to a constant times g of n, which is a big omega lower bound. Conversely, if even the worst case is within a constant multiple of g of n, and even the best case is at least a constant multiple of g of n, then all inputs are trapped between those two constants. Hence, theta of g of n overall. So let's look at that a bit more rigorously, right? So let some function t of I, capital T of I, denote the running time on input I, where the absolute value of I is equal to n. Let's define t sub worst of n to be equal to the maximum of which I is equal to n of t of I. And t sub best of n to be equal to the minimum where I, let me just scoot back a bit. Okay, there we go. Where the absolute value of I is equal to n of t of I. Okay? Let's define these two things, and I'm going to erase the board so that way I have more room to write more things. So we have those two things defined. Now let's assume all running times are asymptotically non-negative. And g of n is asymptotically positive. So it said if and only if, which means we have two things to do mainly, which is left-right implication and left-right implication and right-left implication. So let's start by supposing, well, let's suppose the running time is theta of g of n. Then there exists c sub 1, c sub 2 greater than 0, and n sub 0 or not, such that this is an interesting case. I'll have to look up what most people say, n sub 0 or n sub naught, whether or not people say one or the other more. Okay, n naught, I'll just stick to n naught for now. N naught such that for all inputs, I with the absolute value of I being equal to n greater than or equal to n naught, we have c sub 1 times g of n is less than or equal to t of I, which in turn is less than or equal to c sub 2 times g of n. Now, taking maxima, I said maximum, but earlier, but taking maxima over I yields t sub worst of n is less than or equal to c sub 2 of g of n for all n greater than or equal to n naught. So t sub worst of n is within big O of Gn, right? Now, taking, come on, taking minima over I yields T sub best of n to be greater than or equal to C sub 1 times G of n for all n greater than or equal to n sub 0. So, n naught. So, T sub best of n, well, that's contained within big omega of G of n. So there we have it for the right-left implication. Left-right implication, sorry. Now let's go the other way. So conversely, suppose T sub worst of n is less than, well, no. T sub worst of n is contained within, is within big O of G of n, and T sub best of n is within big omega of G of n. Let's suppose both of those to be the case for this implication. Now, then there exist constants. There exist constants C sub 2, C sub 1 greater than 0, and n sub 2, n sub 1, such that for all n greater than or equal to n sub 2, T sub worst, one second, let me check to make sure my reasoning is correct. Yeah, T sub worst of n is less than or equal to C sub 2 times G of n, and for all n greater than or equal to n sub 1, T sub best of n is greater than or equal to C sub 1 times G of n. Now let's set n sub 0 to equal the max between n sub 1 and n sub 2. What we get is that for any input I, capital I, of size n being greater than or equal to n naught, C sub 1 times G of n is less than or equal to T sub best of n, which is less than or equal to T of I, which is less than or equal to T sub worst of n, which is less than or equal to C sub 2 times G of n. So every T of I is sandwiched, very formal term there, but it's true between constant multiples of g of n. Therefore, therefore the running time of the algorithm by definition of theta is theta of g of n. And so we have their equivalents. We have our if and only if case, completing exercise 3.2-5. Still got time for exercise 3.2-6. May be able to knock this out in one go. Let's see. So, for exercise 3.2-6, we are told prove that little o of g of n intersects with little omega of g of n is the empty set. Has to prove that this is the empty set. So, weird thing to kind of ask for an algorithm in an algorithm analysis textbook, but I mean it's there. I suppose it serves its purpose. So intuitively, little o means strictly smaller order, right? So f eventually becomes smaller than every constant multiple of g. Little omega means strictly larger order. F eventually exceeds every constant multiple of g. A function cannot be eventually less than every constant multiple of g, and also eventually greater than every constant multiple of g. So that's a problem, right? Well, not really a problem. This is literally a problem. It's an exercise, but let's get into talking about that more rigorously. Well, assume for contradiction that there exists f with f in little omega of g and f in, did I say little omega? Little o of g, and f in little omega of g. So by the definitions, they're on sale, no, but by the definitions, and with g asymptotically positive, f being in little o of g means, okay, for every c greater than 0, there exists n sub 1 such that o is less than or equal to f of n, which is less than c times g of n. And this is, of course, for all n being greater than or equal to n sub 1. Now, what does it mean for f to be in little omega of g? Well, what that means is for every c greater than 0, there exists n sub 2 such that 0 is less than or equal to c times g of n, which is less than f of n for all n greater than or equal to n sub 2. Now let's take, well, I'm going to need more board space for this eventually, but for now let's take c is equal to 1 in both statements. And I'm going to erase the board so that way I have more room. Okay, so if we take c is equal to 1 in both statements, then there exists n sub 1, n sub 2, such that for all n greater than or equal to n sub 1, we have f of n is less than g of n. And for all, so, and for all n greater than or equal to n sub 2, we have that g of n is less than f of n. Now let's take care of this a little bit. So let's let big N be equal to the maximum between n sub 1 and n sub 2. Now, for all n being greater than or equal to n, we must simultaneously have, may not be proper English, but it helps to emphasize a point, simultaneously have f of n is less than g of n, and g of n is less than f of n, which is a contradiction. So, no such function f exists. Therefore, little o of g of n intersecting with little omega of g of n is equal to the empty set. There we go. That's it for 3.2-6. Now let's go to 3.2-7, which is the last of the 3.2 exercises. All right, so for 3.2-7, what do we have? Well, we can extend, it says we can extend our notation to the case of two parameters n and m. N is for neat, m is for monkeys, right? Just in case if you couldn't hear me say n and m, because those two are very similar, similarly sounding. What is it? No, there's a better way to phrase that, but that's not the point. But that can go to infinity independently. At different rates. So for a given function, g of n and m, we denote by big O of g of n of m. The set of functions, the exercise itself is taking up a lot of whiteboard real estate here. But the set of functions, big O of g of n m to be equal to the set containing f of n m such that there exists c greater than 0, n not greater than 0, m not greater than 0, such that 0 is less than or equal to f of n m, which is less than or equal to c times g of n m for all n greater than or equal to, for all n greater than or equal to n naught, or m greater than or equal to m naught. And this asks us to give corresponding definitions for big omega of g of nm, and you guessed it, theta of g of nm. Okay? So intuitively, with two independent parameters, the asymptotic bound should hold once either dimension is sufficiently large, matching the given big O convention. So to say big omega mirrors big O with the inequality reversed, we can do that. And we can also likewise do theta requires both bounds simultaneously. So let's go ahead and do that then. We have the definition. This is a matter of copying and pasting and switching the signs for one of them and extending the signs to another side for another, for both sides for another. So let's approach big omega first, since that's what was given to us. Well, that's what was not given to us, but stated first. So this would be equal to the set containing, so big omega of g of nm is equal to the set containing f of nm such that there exists c greater than 0, n not greater than 0, m not greater than 0, such that O is less than or equal to c times g of nm, which is less than or equal to f nm for all n greater than or equal to n naught, or m greater than or equal to m naught. Okay? Now how about theta? Now theta of g of nm, that is equal to the set containing f of nm such that there exists c sub 1 and c sub 2 greater than 0, n not greater than 0, m not greater than 0, such that O is less than, 0. 0 is less than c sub 1 times g of nm, which is less than or equal to f of nm, which is less than or equal to c sub 2 times g of nm for all n greater than or equal to n naught, or m greater than or equal to m naught. Thus completing our definitions there. They're in completing 3.2-7. They're in completing all of the exercises for 3.2. And we'll pick up with exercises for 3.3 in the next video.